Hello, my name is Ross St. Clair. I'm the founder and CEO of Jupiter Hydro, and we're bringing an update to our situation in Nova Scotia and the Bay of Fundy. Before you see a model that I built to demonstrate our 2 megawatt tidal turbine, where each screw has 500 kilowatts. Quite a large unit coming down the pipe. Now this little unit you can see on this video. This is our little turbine in a stream in Dartmouth. As you can see, there's 2 screws one direction and 2 the other. This is moving along at about a ½ meter per second. The speed in the Bay of Fundy is 10 times that, at 5 meters per second. Just thought I'd show you how our new model works. It's pretty horrendous. Nobody's ever made anything work there, so we're excited to show them how it can be done. Okay, now this leads right into hearing from Ray Hunter, who's a world-class expert. I'm happy to be with Ray Hunter, who has known of the Jupiter technology since 2016. He's written 2 reports for ORE Catapult, and he's as knowledgeable as anybody in the world around the tidal energy industry. It's great to see you again, Ray, and thank you for all your tremendous support over the years. Just say in your words where you think of where Jupiter's at, where we've come from, and why we've got a better mousetrap, in your opinion.
Yeah, well, as you know, Ross, I've been kind of a reasonable supporter of your general line of travel for quite a few years now, and that kind of stems from the very early tidal devices that came to market. Now, these were backed by large established OEMs, companies with great capability, and they were backed by significant financial resources. But what they utterly lacked, in my view, was any imagination and any recognition of the environment in which the devices were going to be operating. Now, to be fair to those OEMs, I discussed this issue with them many times, and they said, well, investors don't like risk, and they know what a wind turbine is. So what we are giving them is a wind turbine on the seabed. And for various reasons, all that resulted in was very expensive equipment that nobody could afford. Equipment that didn't perform well, equipment that was exceedingly difficult to maintain, exceedingly difficult to deploy, and which didn't use the force regime at all, kind of insightfully within the environment of the ocean rather than the environment of the air. And unfortunately, the cost of these devices turned out to be extremely high. And that ultimately did the industry a great deal of harm, because it said tidal energy doesn't work, tidal energy is expensive. And that was a wrong conclusion. Now, in the meantime, smaller companies like Jupiter were looking more closely at what the right approach would be, the principles would be in operating a tidal device in the ocean, not a wind turbine in the air. And that concluded very early on that what you should be doing is not adopting expensive subsea engineering. You should be adopting surface-based marine engineering. It concluded early on that you shouldn't be in the strong shear layer on the seabed where there's very little resource and what there is very turbulent. You should be higher up in the water column. And a whole host of issues like this were being thought through by small companies that were seen to be going against the grain, whereas in reality, it was the big companies who were going against the grain of common sense. So Jupiter were going in the right direction, and they went further than just kind of taking a wind turbine and suspending it from a vessel. They were looking far more closely at the maintenance requirements, and that in part led to looking at the Archimedes screw, which kind of for people involved in renewable energy for a long time was a bit of a, wow, that looks a bit strange. But the more you look at it, it's got a number of nice features. It spreads load. It performs surprisingly well over a range of flow speeds. But importantly, it operates at an angle. And operating at that angle, unlike a conventional horizontal rotor, which is designed to operate in a fixed orientation, the screw has got all kinds of possibilities for power regulation, but it also has the possibility of articulating it up onto the vessel, A, for survival reasons in extreme conditions, but also for maintenance purposes. So that there were a whole host of aspects of the Jupiter technology that just kind of appealed. But they didn't just appeal subjectively to me. In the past few years, the International Energy Agency has published through its Ocean Energy Systems Group guidelines for the development of wave and tidal technology. And part of that is a long list of functional requirements for the design and the conceptualization of wave and tidal devices. And if you go through that list of functional requirements with the Jupiter technology, there's a pretty good narrative actually for every single one of them. So, you know, in fundamentals, I think the Jupiter ideas are very much to be welcomed, and there's good possibility ultimately for a device that will provide affordable tidal energy.
That's fantastic narrative, Ray. I really appreciate it. And you know, the idea of 3D printing and you know, our articulated arm. I've talked to you a little bit about that. So you feel positive about both of those developments if they're backed with really sound engineering kind of thing.
Well, the basic Jupiter concepts, as we've spoken about many times, Ross, are soundly based. They're soundly based scientifically. Now, for long, I've been a proponent of a renewable energy device, a marine energy renewable energy device, needs to be based on sound science, insightful technology, insightful technological approaches, and credible engineering. And a lot of the developments we've seen from Jupiter have been based upon that insightful technology and insightful approach. But it's good to see the technology now moving into the realms of credible engineering. But credible engineering doesn't just mean stuff that has been proven over decades. There's lots of new engineering that is coming to market now, such as 3D printing, which offers tremendous opportunity for all kinds of sectors. So it's really good to see Jupiter embracing the technologies that we've now got with 3D printing. And it's quite clear that, in particular, the rotor, the Archimedes screw rotor of the Jupiter device lends itself to some pretty simple 3D printing, albeit on an impressive scale.
All right, Ray, this is really, really, really helpful. I thank you very much for your input today, and this is going to be very helpful as we go out and find ourselves an investor. We got a lot of them interested now, especially since the SME bankruptcy thing, and the fact that the Department of Fisheries and Oceans has given us a green light. So we've got renewed, you know, a really renewed opportunity to bring in investors now. So your input in this is tremendously helpful. Thank you again, and we'll let you know how it goes down the road.
Yeah, and good luck, Ross. You've been at it for quite a few years now, but keep plugging away. It's well worth it.
Thank you very kindly. Have a great day. Much appreciated.
And you, Ross. Nice to talk as ever.
All right.
As you can see by the last part of what Ray had to say, he thinks the 3D printing idea is a good idea. I'm very excited about it, and we've managed to find a tremendous world-class expert in setting up and making engineering and making these things happen in a very large scale. So with that, we'll go and have the Zoom talk with Jeff Foote.
Here we are with Jeff Foote from Loci Robotics out of Tennessee. And most in the recent few weeks, I've had several discussions and I'm very excited about what Loci can offer us. Can you just give me a little bit of your background, Jeff, and your sense on what I've sent you so far to on the basis of printing our 7.5-foot screw?
Yeah, absolutely. Background, I'm trained as a mechanical engineer, essentially. I've worked in a few different industries. Started out in engineering consulting, doing finite element analysis work for a software company. I did that for a few years and got to work with a number of different companies, largely in automotive and aerospace. And left there and went and got a master's degree, and then went to Boeing full-time for a couple of years, working on their commercial aviation fleet, essentially, doing primarily weight optimization on structures. And after that, I went and taught for 5 years at Tennessee Tech here, fairly locally. Taught primarily machine design and structural analysis there as well. And then joined Local Motors in Knoxville and started working with the large-scale 3D printing there, designing vehicle structures, including primary chassis structures for a small multi-person electric shuttle. And we carried that program from initial design through essentially crash testing. So we took that pretty far. Left there and started Loci Robotics, and that's where we're at now, building the big printers that can do all sorts of different things. And it's kind of a unique fit to what you're trying to do as far as printing the screws. Our printers are based on industrial robotic arms, so they're very flexible and adaptable as to sort of how they reach locations and where they can deposit materials. And by taking our base system, which is an arm with print head on it, and adding a rotary axis to actually turn the screw as it's printing, we're well within the output of the extruder system. We're well within the path speeds that are necessary to keep up with the print. All the math lines up. So printing screws on the scale that you're describing is well within our base technology, essentially.
Okay, fantastic. So in terms of the strength, when I sent you some drag information on the flow rates and all that kind of stuff, so there's different drag on the screw at different rates and all that, you're capable of giving us the strengths that's required and looking at that as well.
Right.
Help engineer that.
Right. Yeah. For most of our base materials, we have pretty good strength profiles already. And then for anything, if we were to decide to go with a different material, I've got several of the local universities that will do strength testing for me to build out the material model that we can then feed into an analysis model. So from running basic hand calculations just to make sure we're not doing anything silly to detailed finite element models to validate the specific sizes and thicknesses of beads, for instance, that would be necessary.
And these beads have got carbon fiber in them, a percentage of carbon fiber, which in a sense gives it the kind of strength it needs. That's the basis of giving it the strength it needs, right?
Sure. Yeah, strength and stiffness, of course. These are short strand carbon fibers, but even at that, I think the average length is around 3 millimeters, but that's still sufficient to boost the base strength of the polymers by a factor of 2 or 3 in most cases.
Fantastic. All right. So the idea of us getting to the place where we go, instead of a 7.5-foot diameter screw, we go to a 25-foot diameter screw laid up on a 4-foot steel pipe. Do you see any major hurdles other than, setting up the kind of right shop we need for all that? Do you see any major blockages around that?
Right, right. Not particularly. You've got to be able to rotate that screw, which would take us into a much bigger positioner than what would be necessary for the scale model. However, the hardware scales quite nicely. The robots could always be put on linear rails to get more reach in either any direction necessary, essentially. So for something that large, you may be looking at a couple of different 2 or 3 robots on rails in order to print in reasonable amounts of time. But at a fundamental level, everything about our system scales quite well to that sort of size.
All right. I think that's all I need from you for now, Jeff. I'm very excited to have been able to connect with your company, and I really look forward to us working with you. My next plan is to get a 10 or 12-inch pipe, put some rotational holes in it like you suggested, bring it down and watch you print it. So one day I'm going to be down your way, and we'll meet face to face and build the 7.5 footer.
That sounds great. We're looking forward to it.
All right. Thank you again for your time. Have a great weekend. It's a Friday now, so have a great weekend.
All right, you too.
So after understanding that we can print these screws with the 3D printer, this is very exciting to me because it basically knocks my budgets for these screw turbines in half, and it means that we have to build a purpose-built facility to make these. But once that's built, my God, what a wonderful way to do it, incredibly cost-effective way to do it. So part of that setup to do that would be done with GRF structures, and GRF structures will be building our steel platform, floating platform, our swing arms, and hydraulics to lift and lower the screws, all that kind of stuff. That will be engineered and built by Greg Farrow from GRF Structures, and so we'll hear from Greg now. I'm here with Greg Farrow, owner and founder of GRF Structures, fabrication shop in Dartmouth. That's 180 feet long. It's got 2 30-ton cranes, and it's an absolutely excellent facility to build our platform and swing arms and all that. Greg, just tell us a little bit about your upbringing and background, and we'll go from there.
Well, I started out in the business working for my father, who had a family business in structural steel fabrication. We had plate rolls and brake presses, and we did all kinds of plate work that would be relating to the fabrication of the platform for Jupiter's technology and the swing arms themselves. So I got a huge amount of experience in a very young age on how to fabricate any of the components that would be in the Jupiter hydro platforms. After I worked for my dad, I went to university, got a degree in civil engineering, specializing in structures. I then finished all of the studies to become a welding engineer. So I know basically how to weld any component that would be in this, can do welding procedures, taking courses in metallurgy and anything that we need to make sure that the structure can be built properly to withstand the harsh environment of tidal. I've been in business for over 20 years, fabricating structures that are on barges, are in marine environments, We did this for Survival Systems Limited that does survival training for the U.S. military, which we've done all over the world.
Well, that's fantastic. What do you think of the new opportunity to join up with Jupiter Hydro?
I'm very excited to be a part of this project. I'm hoping to get started on it very soon.
Well, we sure hope so too. I will say that one of the things, maybe you can go to look at this great, Raphael, this arm here was actually Greg's idea, and it was fantastic idea because I've been very concerned about the power cabling between the surface and the ocean floor, and Greg's idea was that we put the power cable in a rigid tube on a swing arm, and I feel like it solved a major problem that I've been concerned about for many years. So this is the kind of thing that Greg brings to the table, tremendous experience and tremendous creativity in the process, and that's the kind of team member I want. And we're having discussions about joining the two companies, and Greg being a major force behind us moving throughout the world with this technology. We feel like there's huge opportunities to build and deploy these in the UK down the road, and Greg is going to be a major part of that, and I'm really excited about it. Thank you, Greg.
Thank you, Russ.
All right, I'm excited that Greg is going to end up being a part of our team. This is just a huge step forward for us. I want people to understand that we have a power purchase agreement for 2 megawatts with the Nova Scotia Department of Energy through Nova Scotia Power, and that will yield around $40 million over 15 years, which is pretty amazing. And we will have the opportunity to go into other sites in the Minas Channel too, because quite honestly, the other bladed technologies have been blocked big time by the Department of Fisheries and Oceans. And just a few weeks ago, we got a ruling from them that, in fact, this turbine does not harm the fish. So we're the only ones with the green light to go ahead in the Bay of Fundy. This lends itself to unfortunate circumstances for those that build bladed turbines, but incredibly fortunate circumstances for Jupiter. And we are patented with this system in 23 countries. We also are, besides being fish friendly and very robust and strong and easy to maintain, we are 1/3 the cost of our main competitors. And I've got all the material I need to back all that up, and we'd love to talk to any potential investors that want to hear more about it and be part of this exciting opportunity to actually roll out an entirely new green energy technology for the world. Thank you.